Now, ionization states or oxidation states. Elements at the extreme ends of the D series have either too few elements to lose or share, or too many d electrons. That is the reason we saw at the extreme ends of D series lower number of oxidation states. For scandium, it has shown only +3. Scandium trichloride. Next element, we having the titanium. It shows +2, +3 and +4. But +4 is relatively greater, having greater stability, because after +4 it loses all the electrons and making a strong covalent bonds. TaCl3, titanium tetrachloride, titanium dioxide. These are few compounds. Remember that titanium tetrachloride is used, if you remember, in the isolation of elements, purification of elements. TaCl4 is used through vapor phase refining. TaCl4 is in vaporous phase. After it's purified, it's taken out, broken back to be pure titanium. Similarly, titanium dioxide finds its application in pigments, in paint. Next is vanadium. It shows +2, +3, +4 and +5 oxidation states. These are certain compounds like vanadium pentoxide, sodium metavandate, sodium orthovandate Na3VO4, vanadine sulfate VOSO4, VO2 positive acts as a divalent cation and SO4 negative, ammonium metavandate VO3 single negative +5 oxidation state. These are few compounds of vanadium. Chromium. The elements with large number of oxidation states occur either in the middle of each series. Here in the 3D series, chromium we know having 6 unpaired electrons. That's why it shows up to +6 oxidation states. Like we having the chromium oxide, Cr2O3, chromate ion, dichromate. These are few of the examples of +3, +6. This is chromium negative +6 and dichromate +6 oxidation states examples. Next, manganese, it shows up to +7. Manganese dioxide and potassium permagnate show +7 oxidation state. These are few examples of manganese. Manganese dioxide is +4. Manganese also exists as Mn2 positive, which is divalent oxidation state, extremely stable, and permagnate. It is extreme end, and that's why it is strongly oxidizing in nature. Manganese dioxide is used in lead-acid batteries, dry batteries. Many dry batteries that we use having a manganese dioxide in it. We use potassium permagnate either in our analytical labs or as a disinfectant also it is used. Iron +2, +3, +4 and +6 oxidation states do exist for it. For cobalt, +2, +3 are having better stability. Nickel +2, +3, +4, +2 and +4 are more stable. Nickel exists as a nickel sulfate, which is also used in plating industry to plate our components. Copper exists in +1, +2 like cupric chloride, copper dichloride. Zinc exists in +2 stable oxidation state. zinc chloride, zinc oxides. Many examples are there. Another point about oxidation states. In D block, for group 6 elements, that is molybdenum and tungsten, we find +6 oxidation state is more stable compared to chromium +6 oxidation state. So we are talking about group 6 elements in D block. What we will find, this chromium in 6+ oxidation state is having a lower stability compared to molybdenum and tungsten. That is the reason we are having a molybdenum trioxide and tungsten trioxide as having greater stability compared to potassium dichromate. Potassium dichromate is a strong oxidizing agent. The reason for this is molybdenum and tungsten having greater size, so it can better stabilize the higher charge compared to small size chromium. Another is, we know now in the D block elements, another unique property is to show zero oxidation state complexes. These low oxidation states are found when complex compounds has ligands that are capable of showing pi acceptor characteristics in addition to sigma bonding. For example, we are having a nickel tetracarbonyl, iron pentacarbonyl. Both of these compounds are in zero oxidation state. Here what happens? Carbonyl group makes a sigma bond with nickel using its d orbital. Further, nickel forms a back bonding or gives electron back to the carbonyl group through its overlapping with p orbital of carbonyl, which may act as a pi acceptor. That's the reason even in zero oxidation state, nickel can make a complex. Similarly, same complex happen with a iron carbonyl. Carbonyl makes a sigma bond with iron, and iron donates back electron to the carbon p orbital of carbonyl group to make a back bonding, which is because of the pi acceptor characteristics of carbonyl carbon. Feasibility of oxidation states. Feasibility of reaction depends on the transformation of the solid metal atoms to the +2 ions in solution. So how the reaction will happen? That depends on the formation of these ions in solution. It will happen because of 3 factors. First, we have to convert the solid into atoms. Bulk of the solid have to be converted into atoms through atomization. Next, we have to ionize them. Finally, through enthalpy of hydration, those ions are stabilized. First 2 factors, enthalpy of atomization, the process of converting the solid metals into its individual atoms, requires energy, it's positive. Second process, conversion of these individual atoms into ions, like copper 2 positive, is enthalpy of ionization. Both requires energy. That's why their delta H is positive. Third step, hydration of these ions in solution. This is a process which is provide the energy to compensate for the first 2 steps. And what happens in case this energy is not sufficient? What we'll see the reaction is not feasible, like for copper. if you put a copper directly in water, it will not be converted into copper-2 positive ions because hydration energy is low. That energy is not able to compensate for its atomization and ionization. Stability of higher oxidation states. What we saw, beyond manganese, no metal have trihalides except iron trihalide compounds with chlorine, bromine, and we exist to have cobalt trifluoride. The ability of fluorine to stabilize the higher oxidation state, only we saw trihalides for these compounds, to cobalt and iron, for iron 2 for 3 only, for fluoro group, chlorine and bromo group. Then we having another compound, cobalt trifluoride. Still, why fluoride is able to stabilize the higher oxidation states? Reason is, first, high lattice energy. Smaller here, it is fluoride is small in size, and that's why it's able to provide a higher lattice energy. Next, the bond enthalpy in terms of higher covalent bonds, the VF5 and chromium hexafluoride, that is may be responsible for that fluoride group having a better tendency to stabilize higher oxidation states compared to these for other groups like chloro, bromo, or iodo. Remember that fluoro group is very small in size. That's why it's having high electron density as well as small in size. And it can, steric hindrance also plays on role while stabilizing the compound. Let's look at all these oxidation states for 3D series one by one. First, titanium. X means we are talking about all these halides, right from fluorine to iodine. So titanium for +4 for all, +3 for all, but difluoride only for chloro, bromo, iodo, large sized, not for fluorine. Vanadium having a VX4 and VX3 it will show, VX2 it will form. Next is chromium. Chromium form we have all fluorides, chromium hexafluoride, pentafluoride. The reason is small size chromium can accommodate only fluorine around it in hexavalent state because of accommodating 6 big iodine or bromide anions across small size chromium is not feasible for such a chromium 6 high oxidation state. Same thing goes for the CrF5 because with as oxidation state increases, its size will reduce further. That is the reason as size reduces, it will be difficult for the small size cation to accommodate large size anions around it. But going down the group to chromium tetra halide group, it will be possible to make all from fluorine to iodine, CrF4 or Br4 or I4, because now oxidation state has reduced, meaning it having lower oxidation number, and Cr4 is not that small as compared to Cr6, so it can accommodate all these anions. Same thing goes for all the rest of the chromium halides from Crx3 or Crx2. Manganese, same concept, small size. Then further we having iron and up to iodine don't form with bromine of FeX2, cobalt trifluoride and cobalt dihalide, nickel NiX2. For the copper, we know cupric compound are unstable in +1 oxidation state. Finally, we have ZnX2. Concept of disproportionation, what it is. Like copper compound, let's take an example. They are unstable, we just talked about. Copper 1 is unstable, like CuX. They try to disproportionate under aqueous solution conditions. Here we have when we react copper 2 positive with iodide, we are getting a Cu2I2 plus iodine got oxidized, copper got reduced to +1 oxidation state. But this is under dry conditions. Under aqueous conditions, what happens? Immediately it will disproportionate to give us pure copper in 0 oxidation state and oxidized to Cu2 positive, which is having a better stability. The stability of Cu2 positive rather than Cu single positive is due to the greater enthalpy of hydration of Cu2 positive under aqueous conditions. Cu2 positive having greater hydration energy, which is good enough to compensate its ionization energy required to remove the second electron. Next is ability of oxygen to stabilize high oxidation states exceeds that of fluorine because oxygen makes multiple bonds with the metal. Thus, the highest manganese fluoride is Mn4, while for oxide it can make Mn2O7. In the covalent oxide Mn2O7, each manganese is tetrahedrally surrounded by oxygen atom to make MnO-Mn bridge. That's what happens here. Manganese having a tetrahedral position of 4 oxygen atoms. Here is Mn4, which is tetrahedrally surrounding the manganese. Next is oxidizing capacity of 3D element oxides. You'll see here from vanadium ions to dichromate to manganese permagnate. The trend is due to increasing stability of the lower species to which they are reduced. So on what factors the oxidizing power of these species depend, like MnO4 negative, permagnate, dichromate, followed by vanadium. This is a U2 positive. Now these vanadium ions, why it is so? It depends upon the factor that to which species they are reducing, and then what is that standard electropotential for that reaction. Let's see. It got reduced to VO2 positive. So from +5 oxidation state it goes to +4. Dichromate goes to +3 oxidation state from +6. And permagnate from +7 to +2. So looking at it, the relative standard electropotential for this MnO4 is far greater compared to this vanadium ion.